You will utilize ultraviolet visible spectroscopy in several experiments this semester. This experiment explores the relation between an absorbing species that imparts a color to a solution and the absorbing species' concentration. The color of a water solution that contains the absorbing species tris-orthophenanthroline iron 2 is red-orange. This complex consists of 3 orthophenanthroline molecules, or ligands, attached to an iron 2 ion, which is located in the center of the complex. You will prepare this complex, which is also called ferroin, by reacting an excess of orthophenanthroline with a known amount of iron 2. After preparing the initial stock solution of ferroin, you will take the visible spectrum to determine the wavelength of maximum absorbance for this complex. This wavelength of maximum absorbance is called lambda max. You will then write a short experimental procedure detailing how you will create 4 more solutions from the stock solution, so you have a set of 5 solutions all containing different concentrations of ferroin. You will then measure the absorbance of each of these 5 solutions at lambda max and graph the results in Excel. A solution of known concentration of iron 2 is reacted with a solution of known concentration of orthophenanthroline to form the ferroin complex. The characteristics of this reaction are a 1:3 stoichiometry, only the product imparts any color to the reaction solution, and when forming ferroin, an excess of orthophenanthroline is added, making iron 2 the limiting reagent in forming this complex. This reaction is actually in equilibrium, and by using an excess of orthophenanthroline, a relatively accurate and straightforward calculation can be completed to determine the concentration of ferroin formed, derived from the amount of iron 2 initially present. The structure of orthophenanthroline contains 3 rings of carbon atoms and a pair of Lewis-based nitrogen atoms. Each nitrogen atom can donate its basic electron pair to a transition metal, such as iron 2, to form a dative bond, so named because the nitrogen donates both electrons to the iron in forming the bond. Each orthophenanthroline ligand can form 2 dative bonds to the iron by using nitrogen atoms. The orbitals on iron 2 which receive these nitrogen-donated electron pairs are of the appropriate size and location such that 3 orthophenanthroline ligands can bond to the iron. This is responsible for the 1:3 stoichiometry in forming the product. Here is the structure of the tris-orthophenanthroline iron 2 complex, showing the arrangement of the 3 orthophenanthroline ligands around the central iron ion. Since there are 2 nitrogen atoms that form dative bonds with iron, orthophenanthroline is called a bidentate ligand. The ferroin complex has a +2 charge, so it is soluble in aqueous solution. In this experiment, the counterion is sulfate. The measurements of this experiment involve following the prescribed procedure for making a stock solution of ferroin. This is completed by reacting a known volume of Fe2+ with an excess of orthophenanthroline. Note that the concentrations of both reactants are the same, which should facilitate the calculation of the excess amount of ligand needed to form the complex. The concentration of the ferroin product in the stock solution is then based on the starting volume and concentration of the iron 2 used. The stock solution is used to determine lambda max. This wavelength will then be used to compare the absorbance of solutions of ferroin with differing concentration. You must formulate a procedure for preparing 4 additional solutions from the stock solution. Either your TA or the lab instructor must validate your procedure before completing it in lab. Using samples of your stock and the 4 prepared solutions, you will then determine the absorbance of all 5 solutions at lambda max. These results will then be graphed on Excel, with the concentration on the x-axis and absorbance on the y-axis. This graph is then used to determine if any relationship exists between the concentration and absorbance of these ferroin solutions. The UV-Vis spectrometer you will use to make your absorbance measurements is the Evolution 60. It can be operated either remotely by computer program or directly by using the controls on the instrument itself. The computer program is Vision Light and runs on an adjacent computer interface to the spectrometer. The sample carousel holds at most 5 samples and a blank, which will be deionized water for this experiment. For the visible scan to determine lambda max, the carousel will contain only the blank and a sample of the stock solution. When completing the individual absorbance measurements at lambda max, the carousel will contain a blank and a sample of all 5 prepared solutions. The color imparted to a solution by an absorbing species is a result of the absorption of visible light by the excitation of electrons. For transition metals, this is d electrons. As an example of an absorbing species, the visible spectrum of azidopenylamine cobalt-3 is shown below. The lambda max of this complex is 517 nanometer, but it absorbs light between 400 and 580 nanometer. By absorbing most of the light between 400 and 580 nanometer, the remaining transmitted light is a combination of violet, purple, red, orange, and yellow. The combined visual effect of the transmitted colors of this complex is a dark red wine color, although putting a color label on solutions in lab can be challenging. This experiment is completed in pairs, so you will have to work together to devise an experimental for the 4 additional ferroin solutions prepared from the stock solution. Print 2 copies of the UV-Vis spectrum of the stock solution that's used to determine lambda max. Record the absorbance reading at lambda max for all 5 solutions. Your lab write-up will include an Excel graph of your absorbance concentration data of all 5 ferroin solutions. Other details of this write-up are in the experiment.